what I want to make sure that everybody's aware of is, as we test these various manufacturers' technologies, we are no means saying that those devices don't have their place and don't have function and value in the marketplace. What we're merely saying is there's a design characteristics that are not very conducive to eliminating those switching transients. And so we want to focus our energies in, the Industry 4.0 world on being able to eliminate those switching transients. Our Tektronix scope here will capture the surge that comes out of the surge generator, and the probes are connected up to a trigger mechanism to capture that wave. These indicators here on the screen are different volts per division. And as we go along in the testing, I'll change them so that you can see more or less of the sine wave and more of the transient. So we're going to start with this metal oxide varistor. And what I want to do is inject 2000 volts and 67 amps on a ring wave into the zero crossing of this MOV. And we'll look at this let-through voltage and then a couple other characteristics. So this is 2000 volts, oscillatory ring wave at zero crossing of the sine wave. Okay, so if we take our cursor to the top of the wave, and we got quite a bit of noise on the line here, but we'll go right to that insertion point. And what we see at this point is a residual voltage of 294 volts. And obviously a significant portion up and down the sine wave. And when you see this on a transient or on a wave shape, we typically want to think of, okay, it's just straight up and down. But as we expand the time base out, you can actually see its oscillation. And you can, very plainly can see that there's 1, 2, 3, 4, 5 different zero crossings of that sine wave. So whereas the voltage level has been kept fairly low, there's still this significant amount of transient below the sine wave itself. So let's take this off of the table. I want to show you now we'll talk a little bit about our series versus our parallel and how key and important installation is. So this is our STSBT unit or SPW unit with wires. We have series connection ones, and we also have them in parallel with wires or terminal strips. But the key important thing is internally, the surge components are in parallel, so that even if the unit were to fail, the power is still going to get to your connected loads, and the customer can still keep his process running. It's not going to turn off his process. But what I want to show you is the difference between the series connection, the parallel connection, and the residual voltage. So we're going to surge test the input, and we're going to put our probes on the output and take a look at the let-through voltage performance. This is a unit you put on PLCs, control cabinets, fire alarm, burglar alarm, elevator controls. So let's look at the same configuration, the 2000 volts, we'll just stick with that. I'll dial it down a little bit, and you can see how it just like takes everything off. So see, the power's on, and we're doing the line to neutral. I'm going to go down to 50 volts, but look, got about 24 volts. Let's see if I can dial it up a little bit better. We can see it. Dial it down to 50 volts per division. And hit it again. Okay. So now in the series connection, there's a little tiny peak of that, and that takes us to about 18 volts. Let's zoom up here and you can see that. So we're at 18 volts. Now, what I want to do is I'll pull the surge generator off. And these leads are about 27 centimeters. Our optimal installation is, we recommend 15 centimeters or 6 inches. And so I'll show you what the difference is in performance just with about 10 extra centimeters of wire. Cap this off so nobody like me shocks himself. No fun at 9:30 at night. So we'll leave that right there. So we'll now test it in parallel because the units, the surge components are in parallel inside. Now, look how much the let-through voltage has changed from 18 volts. I've gone out to about 47 volts just with the extra added wires. Now, people say, why do you make such a big deal of installation? Why is it so important? This is why. Because let me show you this also. If you'll notice, we've got about 8 volts or so below the sine wave. Now we do have a false zero crossing. And the client says, yeah, this stuff is no good. I told you it wouldn't work. And we walk out there and we find 45 centimeters of wire on there. You're right. It's not going to work. So what do? What we've discovered is if you'll take wires and simply on the single phase, the phase in neutral, and just twist them together, a couple, 3 or 4 twists if possible. And we'll see now what kind of change we get in the residual voltage. Now, I try to be very careful. You'll see the black part on the table there. I wasn't so careful one time and blew something up and threw breakers here, and everybody's running back here trying to find out if Jeff's dead or alive. Okay, let's zero that out. And we'll look what the difference in performance. All we've done is twist the wires. Oops, sorry about that, guys. So now look how far down it's dropped. We're at what, about 47 volts? Just by twisting the wires, or 42 volt, we're down to 30 volts. That's how important and critical proper installation is. And now notice, it's difficult to tell. There may be a little tweak there, but it's hard to tell with the noise on the line if there's actually anything that's gone below the sine wave, which you can't see. Sorry about that. There we go. So that's how critical installation is.